Hi everybody, sorry about that. It looks like the tablet is working now. I don't know, some days it just doesn't want to be a tablet. Like, today it just decided that, like, nope, no worky today. But it totally works now. See, I can draw all over the place. There we go, it works. Hooray. What was I saying? We're trying to build up towards this topic right here. Is our objective here. So this last section is a little bit more about quantum mechanics and wave theory, because while light behaves like a wave, what we're going to discover here is that electrons also behave like waves, and we're going to use that information and sort of synthesize it all together to understand how exactly these wave functions work, without doing any math or calculus, because the calculus is extremely complicated. Like, I can't do it, because I haven't done calculus in 10 or 15 years. I can look at the equations and tell you more or less what the pieces are, but, like, I throw that in a solver if I have to. So we're going to look at a little bit of that stuff. Well, so what the heck do we mean by quantum mechanics? Like, I've been saying this word over and over and over. What does it mean? So the mechanics that you are familiar with are called classical mechanics. In other words, if you throw a ball with a given velocity and a given angle to your throw, so like maybe you throw it straight up, or maybe you throw it at a 45-degree angle, or maybe you're bowling and you roll it along the ground. With those variables known, you can predict where the ball will traject in a very reliable and predictable fashion. So if you like set up a cannon and the cannon fires a ball at 10 meters a second every single time with minimal error, the ball that travels from the base of the cannon when it's fired to where it lands should have almost no error to it, like with ignoring things like wind and stuff like that. So things like Newton's laws of motion and the equations for work and energy are examples of classical mechanics. Classical mechanics follows regular rules because macroscopic objects follow regular rules. The random nature of other forces acting on them is not enough to significantly displace them. For example, in the cannon example, I mentioned wind. A little bit of wind in any direction, or even a lot of wind, is not going to displace a ball and completely randomize its trajectory. It may affect it slightly, though. When you're working with teeny tiny objects, though, any sort of energy that you displace into the system, whether intended or accidentally, completely transforms the system. We're going to see a consequence of that when we talk about the Heisenberg uncertainty principle and Schrodinger's cat and stuff like that. But suffice it to say, objects that are tiny, such as atoms or smaller, they follow a different sort of set of rules, and those are called quantum mechanics. Quantum mechanics do not follow typical trajectories and stuff. What that means is that because our objects are so tiny, we can't definitively say this is where it will go. All we can say is draw a region and say, oh, our object is somewhere in here with X probability. Usually the threshold that is used is like 95 or 99. And so the outcome should be similar to classical mechanics, but it's not going to be exactly that. And you're going to see what I mean in some of these very bizarre examples that are going to come up. To help us understand these examples, let's talk a little bit more about waves. If you have waves of any sort of medium, so this applies to light, this applies to electrons, this applies to water. If you have two waves that you sum together, the result is a bigger wave. Now, if you have seen this in action in like a wave pool, where you get the waves to go just at the right sort of frequency, and then when they rebound and your waves that you're making go with them, they get bigger and bigger and bigger. If you were a kid and you like splashed in the pool and you did it just right, the waves would get bigger and bigger and bigger and bigger. Or by pool, I also mean like bathtub, probably, because the bathtub is smaller. Hopefully you don't sit there in the bathtub and go, hee hee, or maybe, hopefully you do. I mean, it's a rough world out there, right? You do you. But I do a video of showing these waves interfering with each other. It's hard to see the constructive interference, but it's easier to see destructive interference, because if I have two waves that have matching peaks or valleys, the result is summed together. But if they have opposite from each other, then the result is neutralized. Sorry, I had to cough there. I need to drink more water. There we go. So these phenomena are called constructive and destructive interference. And those terms themselves, not super important to know. It's just important to know that these phenomenon exist. Waves can be added or subtracted. But what I mean is, when I say subtracted, I can add offset waves to each other. So really all I'm doing is addition. Another interesting property of waves is that when waves hit a corner or an edge of a barrier or some sort of blockade, normally they would just bounce off and the energy would disperse in the opposite direction. But if there's an opening, they tend to spread from that opening if the opening is narrow enough. If you have a corner, the energy will dissipate around the corner a little bit too. This is why if like I shout at you around a corner, you still hear me. My voice does sort of bend around the corner because sound is a pressure wave, and that pressure wave will behave like all waves do. They diffract around corners. Now, if you put two of these slits together, you get a very interesting phenomenon. There's my link that I'm looking for here. But we're going to see that in action in this video. Now, I apologize that the quality of this video is not the best. That is the one I want. Let's see here. So we'll hit play. I don't think there's any audio to this, actually. Yeah, there's not, so I'll just hit mute. All right, so what I'm going to try and do is I'm going to hit pause here. So this is a wave generator. What this is a trough filled with water with a very bright screen, or a very bright light shined at a screen from above, and then this camera is filming it from below. So any areas that are very bright, there is not a lot of water there because all the light passes through. But any areas that are dark, there is a lot more water there. So the dark areas, counterintuitively, are peaks, and the light areas are valleys. But that's not super important, just in case you were trying to visualize this. What's more important is that when I have a barrier and I have a small opening in the barrier, the wave that gets there hits this, and you can see it starts to diffract. And there it is in motion. Now, with two of these, you get the same thing. Both slots that we have in here have their own diffraction pattern. But you can see that there are some interesting phenomena that occur where the waves intersect with each other. Now, the end result of this is that if I were to let these waves propagate against a wall, this wall right here, and I had a sensor that detected what the pattern looked like when it hit that wall, you'd actually get a very regular result. This is just those waves zoomed in a little bit more so you can see that. This is just without the corner there, I guess. I don't know. Okay. What does the result look like when you hit the wall? It looks like this. So if you have two waves coming from two different slits that are generated by a diffraction pattern, then the result that you end up getting looks like this over here. So you get this alternating band of where it's developed and then it's not, it's empty, and then it's developed and then it's empty and then it's developed. And so you get this pattern. In other words, what this means is that when you see this, with a phenomenon that develops the film, you have observed a wave. So this is basically... Wait, I haven't seen by... How do you poop on a submarine? Actually, in those recommended videos in there, I randomly just get stuff that I usually watch. So I'm actually surprised that that wasn't just filled with all of the music that I've played this quarter. I do watch a little bit of Smarter every day. I'm not religious about it, though. It's a good program. Let's see here. Yeah, so if you get this pattern, you have a wave. Now, you obviously have to be able to develop the film with it, but we can do this with light. We can do this with other things that will develop the film. But this is basically our wave proof. We can fire something through this double slit experiment, and if that something creates this wave pattern, then we have a wave. What our object is doing is behaving like a wave. So this interference pattern is very useful as just that sort of evidence. Okay, what we're looking at is a wave. So what we're going to do is we're going to try and do this with electrons. And so we should have a really obvious sort of proof here. Now, this should be a double slit experiment, but if I get this sort of pattern on my developed film, then my electron has behaved like a wave. If I get this sort of pattern where it only lights up here and it's completely empty here for the rest of it, then my electron behaves like a particle. And so here we go. This is like definitive proof. We can figure out what an electron behaves as and then use it appropriately. And for a long time, people thought, well, electrons have to be particles. We can see them when we do the cathode ray experiment. The electron goes right across the tube, right? It's a beam. It's a beam of particles. So naturally, we do the experiment, and this is what happens. What the fuck? Huh? How? This is what you would expect, right? If I have a bunch of particles and they hit the wall, they should just kind of stop right here. But if they go through, then I should just get these two lines. And yet if I actually fire electrons through this beam, and it doesn't matter how many I fire, even if you fire one, you still get a wave pattern, which doesn't make any sense. How could one electron go through both slits and make two? It still does. That I can't explain with one. I can explain it with two. But I can't explain it with one. You can fire one electron and you still get the interference pattern. And so what conclusion do we draw here? Well, I guess electrons aren't particles. They're actually waves. So electrons behave like waves, which means that everything we've talked about from this point applies to electrons. So all of the wave behavior is relevant to electrons, which means that an electron going around a nucleus can be treated as if it were a wave, as opposed to a particle going around an orbit. Now, because it's a wave, that means it's going to follow quantum mechanics and have some uncertainty to it. And more on that in a little bit. What we're going to do for this next step is talk about how waves can be measured with a different equation that we're never going to use. So I'm not going to make you calculate this equation. We're not going to do any examples. You're not going to be tested on it, other than possibly conceptually. Now, conceptually, that does mean that you have to know what the numbers mean, but this is just a constant. This is mass. And you might think this is frequency. It totally isn't. Now, for these equations to work, we have to actually put these units in like this. I should actually put like that. There we go. De Broglie wavelength. Yes, it's very healthy. All right. What this means is that depending on what your mass is and how fast you're going, you too will have a wavelength. Now, notice that we're starting with Planck's constant and dividing by mass. So your wavelength is going to be so tiny because Planck's constant is a number that's about this much, and your mass is about this much, so this gets even smaller. And then depending on your velocity, I don't know, we'll say 1 to 10 meters a second, this gets smaller still. So the wavelength that you're going to observe, and this will be in meters, for any macro scale object is so tiny that you will never, ever, ever observe it. No entity that we have access to would be able to observe it. You can't measure the wavelength of something that's 10 to the minus 40. Like, that's not a thing that works. But if you have electrons, electrons are really tiny, and so you're dividing by a really tiny number, which makes the overall value much larger. And if the object is going super, super fast and you multiply these two things together, that definitely has some impact on it. So, with these two things in mind, we can consider that tiny objects have wavelengths that are observable. And so I actually have a calculation for this that I'm just going to show you on the screen so that we can work through it. Would you proceed to occupy the known universe as velocity approaches zero? You have to be moving to have a wavelength. Now, technically, nothing in the universe will have zero speed. You are always moving in some capacity. So we are hurtling around the sun, and we are also traversing through space with a velocity. So that counts too. You're not going to be isolated in a vacuum at velocity zero. Let's look at an example here just to give you an idea of what these wavelengths are. I'm going to do this calculation for you. You don't actually need to. That's what I was expecting. Okay. It's like, where did my thing go? I forgot I had rebooted. All right. And part of the reason that we're not going to have you do this is because it's a bit of unit hell. And as much as I feel like unit hell is... And I know what the mass of an electron is because I can look that up. I believe it's this. Is it 30? I want to say it's 30 kilograms. I need it in kilograms, so I'm going to go look this up. Mass, not NAS, not if electron. 10 to the minus 31. I got the other numbers right, but... Oh, Okay, that's cool. And then velocity, it's going real fast. All right, so what I'm going to do is I'm going to write out all of these units one at a time. So we're going to start with H. So this is going to be H. And I'm going to try and highlight these like this. So this is H. Just so you see where my unit hell is going. Okay, and then so this is going to be 1 over m right here, which we'll write down as this. Oops. And this will be 1 over velocity. And if I multiply these three things together, I should get the equation, right? So the velocity is 2.65 times 10 to the 6 meters per second. All right. And now looking at these units, you're probably thinking like, holy crap, those units are not going to cancel out at all. In fact, my seconds square themselves. What the heck? Well, the next thing that we got to do is we have to define what a joule is. So a joule is the force of a Newton applied over a meter. And a Newton is equal to a kilogram meter per second squared. So if you've taken physics, you know all these things. So 1 joule would just be this times a meter. Or in other words, 1 joule is a kilogram meter squared per second squared. And so what I can do is I can then do this right here. This will just be my conversion for joules. So 1 joule is a kilogram meter squared per second squared. In other words, there's my conversion right there. So if I broke that into 2 terms, for example. So now I can start canceling stuff out. So this joules goes away. This kilograms goes away. Oh, I didn't cancel the other joules, sorry. I get rid of 1 second, 2 seconds on the top. There's a squared second on the bottom. That goes away. And then I have a meter on the bottom and a meter squared on the top cancels out. And the only unit that's left is meters, which is real convenient because that's what we're looking for, right? So if I enter my numbers in this manner, I will get a result that is in meters. And that will be the wavelength of this electron. So let's type that in real quick. And I get 2.74 times 10 to the minus 10 meters. Or in other words, we get this number, and that's totally within the range of things we can observe. Therefore, we should be able to use this to interact with stuff that has 0.2 nanometer light, right? It should be functionally equivalent in terms of its properties that we could measure. And it turns out that it totally is. So you may have heard of a scanning electron microscope or a scanning tunneling electron microscope. And so what those microscopes do is they use electrons to interact with matter based on the fact that their wavelength is something that is known as long as we know what velocity we're firing the electrons at the object we want to investigate. So that's cool. We can use this to behave like light at a specific frequency based on its velocity. So the only reason that we can do this, though, is because this number falls into a range that we can actually access with light. So you could get a photon with this. No, you could get a photon with this wavelength. That's possible. It would be in the UV or X-ray region. Let's look at something that you cannot do that with. I'm going to throw a baseball, and the baseball weighs 150 grams. and I'm going to throw it at 11 meters a second. I can't personally do this. I am certainly not that capable. So we'll go back here and we'll just, oops, that's the wrong one. We'll just change the numbers, right? So we're not working with an electron. We're now working with a baseball. And we'll put it in a different color so you can see what's changed here. All the units still cancel out. Our baseball is not going at 1% of the speed of light anymore. Now it's going 11 meters per second. And when I do this calculation, the result that I get is way, way smaller. That, unfortunately, is not a photon that we can observe. That would be a photon that has so much energy in it, like it would destroy any detector we have. So large objects have very, very, very tiny wavelengths. So tiny, you just can't notice them. So why do we really care about that? We care about it for small objects to show that, hey, they behave like waves and we can observe them if they fall into a region where we would normally observe things like light. So we aren't just observing light when I detect something with this wavelength. We're picking up anything with that wavelength, really. All right. That's really all I care about the de Broglie wavelength, is just to show as proof of concept that, like, anything with a particular wavelength that is acting like a wave can be detected in the same way. And that tiny things have observable wavelengths, big things don't. That's good enough. All right, let's get weird with this. We're going to set up this experiment. And this experiment is a laser beam that is placed in front of my double slit experiment. My electrons are going to go through it, but what I'm going to do is I'm going to let the electron pass through, and then it's going to pass through the laser, and the laser will diffract or do something. It'll bend, it'll light up, I don't know, to show, hey, the electron went through this grating. It went through the left side, and I'm going to fire one electron at a time, and then I will know which slit it passed through, and I should be able to observe it behaving as a wave. So I should be able to see both things, because waves could go through both slits at once, but particles can't, right? A particle could only go through one of these. Well, guess what happens when I do this experiment? My electron goes through, it hits the thing. It doesn't actually go in that direction, though, obviously. It goes towards the detector. And we only develop two spots, right in front of the slits. What's the deal here? What changed between this first experiment, or I'm sorry, this experiment and the one we did previously where the laser wasn't there, to generate a different pattern? Because now our experiment says, oh, electrons behave like particles. But the reason that they behave like particles in this experiment and not waves universally is because right here, when the electron hits the laser here, we change its nature. The energy that is being transmitted through the laser hits the electron and changes its properties completely, right? We don't know what direction it was moving. We don't know what velocity it had, etc. anymore. Now we've given it energy and its state is completely changed. When you change tiny, tiny, tiny particles with a large degree of energy, you completely upend their previous status and give them a new one. So what you were looking for no longer exists. The analogy I like to use for this is, imagine that I am blindfolded in a dark room and all of my students are standing there. And my job is to find them in the dark room. So what I am armed with is a flashlight. So I could point the flashlight at you in the dark room. I can't see where I'm looking, so I'm just pointing it randomly. And I might observe you. So here's me, and we'll shine a flashlight, and I might observe a person. Now, if I turn the light off and then turn it back on, you're still there. The light is very low energy relative to you. And so me shining the light on you in the dark is not going to change your current state. Like, it's not going to cause you to not be there anymore. Now let's suppose, this would be classical mechanics, by the way. Now let's suppose, in quantum mechanics, instead of me using a flashlight to find you in the dark, I use a cannon. With a cannonball and, like, gunpowder and everything. And I fire the cannon and it hits you. Obviously, when this happens, you're going to go sailing away. The next time I fire the cannon in exactly the same spot, you aren't going to be there. And if you are, whoa. I'm impressed. Quantum mechanics is like firing at electrons with cannons. Because electrons are so tiny, anything that you shoot at them, including light, completely ruins whatever state they were in. We are basically bombarding our electrons with cannonballs. The cannon was clearly for self-defense. When it's around week 8 or 9, you'll understand why I employ a cannon. You probably may understand right now, to be fair, because exams just finished up, right? But quantum mechanics is like firing a cannon at electrons. You hit the electron and then it's gone. Now, it's not really gone. It's going to just change completely whatever property or trajectory it has that you were looking for. And so we end up in a situation where you can't measure two things about your electron because the first measurement destroys the state that you were trying to observe in the first place. And so this is called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle just says you can't know two things about an object at once. Because when you make the first measurement, you destroy the state of the object and can no longer observe the second property in the initial state. You're now observing it in a new state. Now, notice that the word is uncertainty and not unknown or completely clueless or something like that. So you can make some prediction, however, there is going to be error associated with that. And the more precisely you know one thing, the more energy that requires, and the more imprecise the second thing will be. And there is a formula that relates these two things together. And I don't know if I show it. Yeah, there it is. We'll go over that in a second. But it's not really important to know the formula. What's really important is that if I am trying to measure two properties of an electron, one being a wave and one as being a particle, I can only ever observe it in one state at a time. That is with current technology anyway. Now, believe it or not, within the years of me teaching this, people have actually sort of made a breakthrough in this, and I believe that if you look this up online, you can find an article where an electron is observed as being a wave and a particle at the same time. However, I could not even begin to explain the physics to you behind that, or what was necessary, other than like extremely low energy photons, is my guess, that still somehow interact with the matter. Maybe like they're firing some other particle at it. I don't know. I've read it. I was completely confused and I mostly forgotten it. But for our purposes, this is going to be true. for any system at the microscale level, microscale being atomic or smaller, if you measure one property, you ruin the current state and can no longer measure additional properties with certainty. The traditional use of the Heisenberg uncertainty principle is to do velocity and position. Sorry, momentum is the mass times velocity part. There is a joke that quantum physicists like to do. It's the quantum physicist dad joke, where Heisenberg gets pulled over by the cops, and the police officer says, "Sir, do you know how fast you're going?" And Heisenberg responds, "No, but I know exactly where I am." Implying that he knows this to a high degree of precision, but there is a lot of error on this one. And then the other part of the joke is that the cop says, "You were going exactly this speed." And then Heisenberg goes, "Well, great. Now I'm completely lost. Thanks a lot." Because now you know this one to a high degree of precision, and now this one is an error. So yeah. The takeaway from that is really that quantum physicists tell terrible, shitty jokes. So, but there are multiple ways to express this equation, and they don't always use position and velocity. They can use other other terms or other variables too. But as one of these gets more precise, the other one has much larger error. And they're related by this value, h over 4 pi, where h is Planck's constant and pi is pi. You may see h bar in your text. H bar is just h over 2 pi. Or in some text, you'll see h over tau. Tau is just 2 pi. How do you know it's 2 pi? Because it's part of the pi. There it is right there. There's tau. See, quantum physicists have terrible jokes. So, what's the takeaway from all this? Well, if you remember at the very start of the lecture where I talked about classical trajectory versus quantum mechanics trajectory, if I'm measuring something in classical mechanics, I have almost no error. The error is going to be very, 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 very small relative to the object, and so my path is very predictable. But in quantum mechanics, guessing the position and the velocity of an object is very difficult to do to a high degree of precision because one ruins the other. So instead what we do is we take a probability distribution and we say, okay, my electron is somewhere in this region right here that I'm defining. And then we give that region a name. And that's the electron cloud. So electron clouds are just probability functions as a result of the fact that electrons are waves themselves, and the Heisenberg uncertainty principle restricts us from knowing exactly where they are. So in an atom, we're never going to draw electrons around the nucleus with the intent of knowing, oh, it's over here exactly. We're always going to draw electrons in general vague terms, in terms of the electron cloud, because that's the best that we can do. We can say with 95% accuracy, the electron is in this region. Now, could the electron be outside this region? Yeah, it could be on the moon. It could be wherever the hell it wants to be, right? But 95% of the time, it will be in this electron cloud. Or 99%, or whatever the certainty is on the image that you are looking at. I actually don't know what the threshold is. I just quote 95 because that's the common one. All right, and that's all just stuff that I just said. So, all right. We're going to call the electron clouds, for our purposes, in this discussion, atomic orbitals. An atomic orbital is just a region in space that we have defined with probability. And those regions follow a wave equation that has several variables in it. And these variables are what go into that equation. Now, I don't know if I've shown you the wave function equation. I know that if you were in the Discord way earlier in the sorry, I can't type, and also wave function of hydrogen atom. I want hyperphysics. Yeah, there we go. That's what I want. If you were in the Discord earlier in the quarter, at random times I will respond to messages at like 1 a.m. and then we will just talk about random shit like quantum mechanics and stuff like that. So you can see the variables I introduced down below. These are the equations that govern the shape that comes out of this. Now, this is 3 equations that we actually have to put together, and so they get more and more complex and convoluted. And then when I combine all of those things together, I get these functions, and already you're just like, fuck off, right? Like, no, I don't want to do any of this shit. Nobody wants this, right? This is absurd. And I don't blame you, right? So, suffice it to say that the numbers that I'm going to introduce to you go into this equation. And this equation is called a wave function. What a wave function is it is just a... So, a wave function is an equation that is a function of 3 variables, so you get a 3D region as a result, and that's our orbital. Wow, I cannot write the letter R for some reason. This is super simplified, right? But for our purposes, that's good enough. I'm going to take these numbers that I'm going to generate, I'm going to put them into the wave function, I will get a shape. Our objective in 161 here is not to understand the math. We want to understand the concept. So, what we're going to do is we're going to talk about what these numbers do, and then what shapes come out. Because the shapes are going to be relevant to us in Unit 5, very briefly anyway. And then a lot of organic chemistry cares about the shapes of orbitals. In fact, knowing about this stuff and how the shapes of orbitals look, believe it or not, that was probably the question on my PhD qualifying exam. I don't have a PhD because I left the program. I hated research. But you have to take an exam to qualify for the PhD program. And they let you study for 2 years at the university. This is at UW. And then you take this test, and it's an oral exam. You stand in front of a bunch of faculty, and they ask you questions about your project. But they also pepper in chemistry. So it'd be like if we were having a conversation just about random shit, and then I ask you questions about chemistry related to that shit, and on the spot you have to answer them. And that's your final. That sounds terrifying, but if you are really competent in the material, and I was, but I didn't know that, it's not scary at all. To me, it was terrifying. But I did learn that, wow, I actually understand chemistry real well, because they asked me a question about these shapes of orbitals, and within 1 second I had the answer, and I just said it. And they all just kind of blinked at me like, you know that? You're the first person we've asked that actually knew that. And I was the only one in my year to pass out of like 16 people. So it was kind of cool. So if you think my exam is hard, I was the only person who passed out of 16 in grad school. Everybody else had to do something extra. They had to do an extra project. I didn't. I got to go straight to the pub and celebrate. We had to drink the champagne that night. That seems like a good place to take a break. We're going to define these numbers in more terms after the break here. So get some more water. Go hug a cat. Go hug Schrodinger's cat. Make sure that your cat is alive. They are both alive and dead until you observe them in the alive state. Because that's how Heisenberg works, right? We got to talk about Schrodinger's cat after the break too. Just why it's actually a physics meme. Like, it's not a real thing. But we'll discuss that in a little bit more detail later on. Just remind me, because I'm going to forget to talk about Schrodinger's cat. All right, I'll go put the Metroid music back on. And I'll see you in 10 minutes. Take care. Hi everybody, we're back. Wind down Meridia here. Man, I haven't played Super Metroid in a minute. I need to boot up a randomizer and play more of it. I promised you Schrodinger's cat. I did remember. Let me open my seltzer here. What was I going to say about Schrodinger's cat? I'm going to mess up who said what, but the gist of Schrodinger's cat was that it was basically a meme. So I can tell you the story about what the meme entails, though. Here's the circumstance. And so, oh, you know what I should do, though? I should draw this. I should draw this on the on here. All right. So Schrodinger's cat was the following situation. I have a box, and inside the box is a cat. There's my cat. My cat is very happy. Looks kind of like a... There we go. Oh, now it looks like a raccoon. Oh, we'll do this. There we go. Now it looks like a rat. You know what? I don't care. It's just a meme, right? Okay. There's my cat. My cat is in a box with poison. So I have this poison beaker that, if cracked open, will kill the cat. Now, there is a mallet on the wall here that is ready to fall onto this beaker and kill it, but only if, and it's attached to a radioactive circuit, that has a 50% chance of going off. So, in other words, there is an isotope in this circuit that has a 1 out of 2 probability that it will fire at any given minute. If it does, the hammer is released, which then breaks the vial, and then the cat will die. And that's not as fun for anybody, right? All right. And so what Heisenberg and Schrodinger said was that basically what's going on here is that if I have a box that I just put over this, and the box is just like, oops, that's too tiny. There we go. Like, I have no idea what's going on here in the box until I open the box, which I can do by doing this, right? Currently, right now, in this state, if I don't have the box open and I don't know what has happened to the cat, because remember, there's a 50% chance the cat will live and the 50% chance the cat will die. Currently, the cat is both of these conditions at once. And it's not until I do this that I can go like that. But I have to do that first before I can make that assumption. And so Schrodinger said that, okay, That is absurd. There is no way that the cat is both alive and dead in a box until I open it and then suddenly it's one or the other. That doesn't make any sense. The cat could be dead long before I open the box. And the key word there is could. We don't really know. So in the meantime, let's interpret it as both. Now, with macro scale objects, that seems really stupid. Like, I am not alive and dead until the stream starts and you talk to me. Like, obviously, I am one or the other, right? And also the cat. Yeah, we had to consider the cat. So with macro scale objects, this sounds really stupid, but in quantum mechanics, this is exactly what's happening. An electron can be both a particle and a wave at the same time until you open the box and look at it. And so Schrodinger's cat was basically just an exaggeration of quantum mechanics. And everybody thought, like, wow, this is really stupid. Like, I can't believe you're proposing that this is how matter behaves. And yet, here we are. So that's Schrodinger's cat and what it means. So now you know what it is. It is not a it's not a reason to kill cats or something like that, or whatever the joke is in Portal. In fact, cats really have nothing to do with it. It's just used as a meme, as an example of how stupid quantum mechanics sounds. But in reality, that's exactly how it behaves. So, all right, we're going to start defining some terms here for quantum mechanics that are going to describe our orbitals. Now, the first term, let's go back to this previous page here, actually. These terms go down in order from largest area to individual electron. So we're going to start from a really big picture of the entire atom and then work our way down to a part of that region we just looked at, and then a part of that region we just looked at, and then finally the electron in that region. So the first thing we're going to look at is going to be the largest sub-region of the entire atom's electron cloud that we're going to look at. And it's called the principal quantum number. We have already talked about the principal quantum number when we were talking about how waves behave. And we said that you could get wave n equals 1, n equals 2, or whatever, and there were n minus 1 nodes, and so on and so forth. Because electrons behave like waves, it takes a little bit more energy for my electrons to live farther away from the nucleus. They are wave states in higher energy. Now, we can interpret that by thinking about how the nucleus works and how energy works. So, if I make this axis right here, this is going to be potential energy. It's hard to write sideways. This line right here, n equals infinity, we're going to call that 0 kilojoules. An electron at n equals infinity has no attraction to the nucleus. They are too far apart to see each other, and thus the electron is not bound. But if I put the electron any closer, so like say here, now there is an attraction to the nucleus. Not ionic attraction, actually. I don't want to say that, because it's not really ionic. This would be electrostatic. If my electron is closer, then it starts to stick to the nucleus. It sees it. And what we do is we say that its potential energy is some number, and I'm just going to assign it a random number. However, that number is going to be negative. The reason that that number is negative is because if I want to, say, remove the electron, I would have to move the electron back up to this distance, right? I would have to provide it with how much energy? Well, the difference, right? And a negative 100 plus 100 is 0. So the numbers on the scale are going to be negative numbers just to show how deep in the electron is, how much energy you have to put in to remove it. Now, the closer you get to the nucleus, the more energy you need to put in to get it out, right? So as n increases, we say that higher values of n are higher in energy. And that's what we mean, is that they have a less negative number when plotted on this scale. So just to get the lingo straight here. So when I say something is higher in energy, this is what I mean. It's higher on this vertical axis, and it has a higher n. Now, there's going to be a lot of lingo and jargon thrown around in the quantum mechanics chapter, and every textbook does something different, which is super frustrating. So I'm going to just sort of introduce terms to you. So other terms that are used for the principal quantum number are also terms like shell. We got shell number and then level. Will we cover latent heat? No, not in chemistry. We might talk a little bit about it in 162 when we do thermo. If you mean stuff like Newton's law of cooling and then temperature transfer, like two objects that are different temperatures, yeah, that's 162. We do that in thermo. Not this quarter, though. Now, if I wanted to take a picture of my atom here, this is sort of a one-dimensional slice, but in reality, what my picture would look like if I drew it out was that if I had, here's the nucleus, we'll do it in purple, because that's the color I've selected. And then my electron cloud would be some region away from the nucleus. That would be n equals 1. And then some distance away further, this would be n equals 2. And so on and so forth. Ooh, that's not what I meant to do. Up to n equals infinity. So we're just going to have these sort of regions. So here's where n equals 1 would be. Here's n equals 2. N equals 3 is the next one, and then so on and so forth. That's going to help us in a little bit when we start talking about shapes. Which shape is governed within an orbital is determined by this quantum number, the angular momentum quantum number L. You do not need to remember. Well, I mean, you do need to know that it's called the angular momentum quantum number, but you don't need to know what that means, other than shape. We're going to talk about shape later, but for now what we need to do is we need to define this number. We've already defined n. N can be any number that it wants to be all the way up to infinity. However, it must be an integer. So n integer from 1 to infinity. I was like, I defined n, I just didn't write it down for you. In fact, you know what we should do? If I could find the cursor. There we go. We're going to make a little cheat sheet here. And we're going to find, that's the wrong end of the pen, n 1 to infinity. And I'm going to define this as a positive integer. All right. And then we'll define L. I don't want to do it that way. We'll do it this way. L is also a positive integer, or it could be 0. So the range of values for L is allowed to be between 0 and n minus 1. In other words, it could be 0, 1, 2, 3, 4, all the way up to whatever n minus 1 is. So infinity minus 1, which is infinity, of course, is the upper bound of this equation. Now, other words that you're going to hear for L will include subshell or sublevel. Keep in mind that L in the font that I use looks kind of like the number 1. This is intended to be cursive L here, I guess. So the values of L. And so, yeah, and down here, that's probably the most important one. I should get that one. 0 is less than or equal to L, which is less than or equal to negative 1, n minus 1. So your L value can be any integer between 0 and n minus 1. So what that means is that for a given value of n, only certain values of L are allowed. So let's go do a few examples here. Actually, I might give you an example right here. Yeah, here we go. So what values are allowed for L equals 5? Well, if n equals 5, the possible values of L would be 0 less than or equal to L less than or equal to n minus 1. Well, n minus 1 would be 4. So the possible values of L for n equals 5 are L equals 0, 1, 2, 3, and 4. Notice that there are n values possible. That will always be true. For any given n, you should have n possible values for L. The number of values corresponds to the number of sublevels. You could think of this as if like n equals 5 was a giant building. Each L is a different floor in that building. So on floor 0, electrons could be in there. On floor 1, electrons could be in there. On floor 2, electrons could be in there, and so on and so forth. Now, we're going to further subdivide each L in just a second here. Or in other words, in our building analogy that I am creating on the fly here, each floor has rooms that can be house electrons. Those rooms are the orbitals that we're going to talk about. So these sublevels are just regions of space that contain orbitals. So we're still getting to that part. But what's important here is to just understand how the numbers work for now. Once we've seen all the pieces, putting these together is surprisingly easy. It's just, can you remember the algorithms that I'm setting up here, where n is any positive integer, and L is 0 to n minus 1, positive integers are 0. What about this next one? M sub L. Oh, we'll come back to this. I'll talk about the letters in a second. M sub L, where the magnetic quantum number is a variable that describes which orientation the orbital has. There are multiple ways for electron orbitals to arrange themselves in space, but they need to not overlap each other because electrons repel. So what the orientation number does is it just says, okay, I have to squeeze this many things in here. These are the ways that I can do that without my electrons overlapping each other. The values of m sub L range from negative L to L. And, of course, I have to do the cursive L thing again, So we're going to go to our chart. We're going to put that on there. We'll get a different color even. So now, these can obviously be negative or positive numbers. It doesn't matter. It can be 0. 0 is allowed. 0 is an integer. And what these each describe are just a closer and closer and closer look at where our electrons live. So in other words, here we can say that this is the level from the nucleus. L is the sublevel within the level, so we've subdivided the level further. And then within the sublevel, we have orbitals. Remember that orbitals are our goal here. We want to find where electrons live. Electrons live in orbitals. We just have to define this in terms that we can explain with quantum mechanics. Now, you might have remembered the Schrodinger equation that I showed you earlier, where I had like 3 variables. One was r, which was radius, one was theta, and one was psi. Maybe it was phi, I don't remember. Whatever. Those basically correlate to these 3 things. So, like, n is just the radius, or how far away you are from the nucleus. L is which angle you are from the nucleus. And then m sub L would be what orientation you are, so that would be the other angle. Now, that's a gross simplification, but you can think of it that way. All right. We're going to take our m sub L example, and we're going to look at n equals 5, and let's write out, let's suppose that if for n equals 5 and for L equals 2, what values of m sub L are possible? So that would be negative L to positive L integers. And so we would say, okay, well, negative 2, oops, hold on. M sub L equals negative 2, negative 1, 0, positive 1, positive 2. Now, there is not a correlation between the number of values that get spit out here just yet. We'll talk about that in a little bit. But what we can say is that each number represents an orbital. Orbital. There we go. So with our hotel analogy here, or our building analogy that we have, the level would be which building this is in. The sublevel would be what floor it's on. And then the orbital would be what room on that floor. And altogether, these give us the address of the electron that we're going to be looking at. Now, you'll notice that there's one more quantum number that we haven't talked about just yet. And that's because that number is thankfully very simple. And it's going to be either positive 1/2 or negative 1/2. And this has to do with a property called spin, which we'll talk about a little bit later. But I did just want to have all 4 quantum numbers on the page. So there we go. Those are our 4 quantum numbers that we care about. So we're going to spend the rest of the period just calculating various instances of quantum numbers, and then hopefully by the end we'll get to the point where we can assemble the electron configuration diagram based on these quantum numbers. That's our objective. All right. Let's suppose that I have L equals 3. What are the possible values of M sub L? And so that would be -3, -2, -1, 0, +1, +2, +3. And you could do this for L equals any number. If L was 5,400, then the possible values of M sub L would be -5,400, -5,399, ... +5,399, +5,400. You just do every integer between the two. All right. So now that we've put everything in there, let's do an example starting from n. Let's write out all the possible combinations of all quantum numbers for n equals 4. So let me do this. Since we don't want to get rid of this up here, this is going to be important to us. In fact, let's just make a new layer. Now I can't delete it. All right. Oops. For n equals 4, what are the possible values of L? L could be 0, 1, 2, and 3, right? How about I click on that so you can see what I'm doing? There we go. What are the possible values of L for n equals 4? L could be 0, 1, 2, or 3. Well, if L equals 0, M sub L can be -0 to +0, or in other words, 0. For L equals 1, M sub L can be -1, 0, or +1. For L equals 2, M sub L can be -2, -1, 0, +1, or +2. And then for L equals 3, M sub L can be -3, -2, -1, 0, +1, +2, and +3. Now, the next thing that we want to do is ask ourselves this question. In the entirety of n equals 4, how many different places can electrons be? How many orbitals are there? And the answer to that is, remember that M sub L is an orbital, right? So, how many different outcomes of M sub L are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And if you've noticed, hey, there's a connection between these two numbers. Yeah, there totally is. For a given n, there are n squared orbitals. This is just how the math shakes out. If I had n equals 5, I would then put L equals 4 down here. L equals 4 would go -4 to +4. That's 9 total entries. 16 plus 9 is 25. 5 squared is 25. It checks out. So we could do this in theory for every n that I get that we cared to do it. We could do it for n equals 1, which would just be this top part. We could do it for n equals 2, which would be these two parts. N equals 3 would be these 3 parts. N equals 4 would be these 4 parts. And you could just keep adding these parts to it as you go down, or as you increase n. It's as simple as that. So that's the gist of how we generate all the possible quantum number combinations. Now, what does this mean in terms of orbitals and shapes and designations? We haven't actually talked about that yet. But we are going to correlate these quantum numbers that we just generated into a 3 quantum number code. And so what I'm going to do is we're going to give a code in the format like this: N, L, M sub L. So for instance, this orbital marked with the star would be 4, 0, 0. And this orbital with the triangle would be 4, 2, +2, or just 2. And then this one with the little doodly-doo would be 4, 3, -3. We're going to use those codes later on, particularly in the sense that I'm going to give you a code and I'm going to ask you which of these codes does not follow the rules. And you're going to have to look at the codes and say, oh, this one can't be this. This one's invalid because this number cannot be this if this number is this, if this number is this. That sort of thing. That's where we're going with that. All right. And there's what we concluded there. I do want to go back to the previous slide for just a second, because now that we have established all the framework, we're going to talk about some other terms that are used in quantum mechanics to describe orbitals. And that's on this slide right here. For a given value of L, a letter is associated with it, and you've probably seen these letters before. So these are all L's. L, L, there we go. So you've probably heard of the term S orbital, or P orbital, or D orbital, or F orbital. What these letters do, these letters correspond to families of orbital shapes. And so what that means is that if I go back over to here, and we look at this, all of these orbitals in this right here are going to have the S shape. All of these orbitals right here, because they're L equals 1, will have the P shape. These will be D. And these will be F. Now, that does mean that orbital shapes get restricted as n decreases. For example, n equals 1 only has access to the S shape. N equals 2 has access to S and P. N equals 3 would have S, P, and D, and so on and so forth. It does go past F, but as you're going to learn in a few lectures, no element that we have on the periodic table has electrons that go further than F. There is G, but G is theoretical. The first element that would occupy a G orbital would be element 121. And we're only at 118, so we have a ways to go before we have an element that is observed to have that. All right. I think that might be the fundamentals. That's a lot of moving parts. So I totally get that this is confusing, but what I want you to do is just practice with it here. And the first task I want you to do is do what we just did for n equals 4, but I want you to do it for n equals 3. Write out all the possible quantum numbers. How many should you get? What was the relationship between n3 equals 3 and the number of orbitals? Use that as your guide to make sure that you found them all. And just do it systematically. Do all the numbers. And then right here, I have a series of codes, which I didn't actually write in code format. I thought I did. One of them is not legal, and I want you to tell me which one it is and why it's not legal. So remember, when I say why, that means explain. Tell me what rule you broke to get that quantum number down there. Okay? Go ahead and try this. I'll give you about 5 or 6 minutes to do it. We'll go over the answers, and I think that's it for today. 1 or 2 more minutes and we'll go over the answers here. All right, let's go over the solution here. Let me clear this really quickly, just so that we're starting with a blank page here. Because in reality, I could have just taken what we had and erased the bottom part and we get the answer, but let's work through it. And you'll notice that I'm doing this in a very regular way. So I write out what I want to do first, and then I do all of the possible L's. And then we work from there. And let me get a different color that's darker than that green there. So that'd be m sub L equals 0 for L equals 0. For L equals 1, m sub L can be -1, 0, and +1. And then for L equals 2, m sub L can be -2, -1, 0, +1, and +2. All right, how many orbitals are there? How many things can I circle? Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that checks out because n squared is 9. So there should be 9 orbitals, and there totally are. So our expectation matched with the outcome. Now, if I had to label these orbitals and give them names, what would I name these orbitals? So these orbitals right here would be called s orbitals because they're L equals 0. And so we would actually call them 3s. These would be 3p. And these would be 3d. And you're going to start hearing these names thrown about, and they just represent all of the possible orbitals in the given sublevel with that label. And really, what I'm just going to try and do over the course of these next few lectures, mostly today's lecture and then tomorrow's lecture, and then probably a little bit more next week on Tuesday, is we're going to just introduce you to the lingo and kind of like an immersion, I guess. So real important, make sure that you are reading the textbook and looking at the practice problems, because there's no math here. There's really not much you can do in way of exercises. Like you could do n equals 2, n equals 3, n equals 4, and write it all out over and over and over again. And you'll learn the rules that way. But when you want to pick up the lingo, the only real way to do that is just immerse yourself in it. And so I'm just going to keep throwing these terms at you. And if you have any questions about what any of the terms mean, like how did you get 3p, then I can explain that. So feel free to ask that. If we go back here, one of these numbers, I guess, oops, that's not what I meant to hit. We just put these on the board here. One of these breaks the rules. So if I scroll up here to get the rules back on the screen, which one breaks the rules? And turns out that the only one that breaks the rules occurs here. Why does that break the rules? Well, M sub L has to be between positive L and negative L. So the range would be -1 to 1. But this is not within that range. So this quantum number does not exist. You cannot have an orbital M sub L equals -2 and sublevel L equals 1. All the rest of them fit the rules. So I'm going to give you a bunch of numbers on the Chapter 3 quiz, which you'll take eventually when we're done with Chapter 3. So just be mindful of that, or make sure you remember the rules and how to do these sorts of problems. I think that that's all that I'm going to do today. Yeah, so we're going to come back tomorrow. We're going to discuss shapes of orbitals and what those shapes mean. The shapes are not going to be super important to us in this class, but they'll mean a lot more when you get to organic chemistry. All right, that's all I got. So I totally recognize that quantum mechanics is like this bizarre sort of out of left field topic. Try to stay on top of it the best you can, and the way to do that is to ask me questions, use the Discord, talk about this stuff, you know, that sort of thing. We're going to be in Chapter 3 for a long time, so make sure that you are asking any questions that you might have. Make sure to get quiz number 6 in tonight. It is last call. I'll see you tomorrow.